Our universe is a vast place of astonishing complexity.
From the fiery inferno of stars to the bounty of life teeming all around us, our existence is one of chaos, of order, and of beauty. But what if I were to tell you that our universe is not a realm of light, but rather one of darkness?
The nature of dark matter is one of the greatest unsolved mysteries of modern physics. Despite making up approximately 85% of the total mass of the universe, it is entirely invisible to all forms of electromagnetic radiation. Its effects, however, are certainly not invisible. Dark matter exerts substantial gravitational forces on normal matter, which drastically impacts the way that galaxies rotate.
Take, for instance, a galaxy with the majority of its matter clustered towards the center, which can be represented as a point with mass m. Now imagine a star located towards the edge of this galaxy revolving around the galactic center at a fixed radius r. Using Newton's second law, we can derive an expression for the velocity of the star, where g is the universal gravitational constant, m is the galactic mass, and r is the radius of revolution. In this idealized galaxy with no dark matter, velocity should be proportional to the inverse square root of r.
When plotted, the velocities of stars far away from the galactic center should look like this.
However, observations show that velocity actually continues to increase with radius, indicating that there must be a lot of hidden mass near a galaxy's outskirts.
So we've seen what dark matter can do, but what is it really made of? The most prominent theory is that dark matter is comprised of WIMPs, that is, weakly interacting massive particles. These particles would interact gravitationally and be abundant enough to give rise to the observed effects of dark matter.
Many experiments seek to directly observe WIMPs using detectors of ultra-pure silicon or germanium that have been cooled to within 30 millikelvin and are surrounded by multiple layers of radiation shielding. When particles collide with the detector, they create minute vibrations in the crystal lattice that are known as phonons. Finely tuned sensors calculate this vibrational energy, as well as the energy from electrons that have been knocked loose.
Because WIMPs don't interact electromagnetically, the ratio of phonon to electron energy should be much higher than in collisions caused by mundane particles such as electrons. This gives us a clear method of isolating WIMP interactions. The WIMP theory of dark matter is just a theory, and it's certainly not the only one. The truth of the matter is, we know very little about this enigmatic substance, other than it's there, just waiting to be explored. But isn't that exploration what makes science so interesting? If everything could be described in just 3 minutes, then what would there be left to strive for? So keep exploring, and maybe in the darkness we can find the light.